now it's almost time. Okay. So today in this session, a very special one, we will have Professor Caron Huot from McGill University. I think Simon is the recipient of this year's Frontier of Science Award. Yeah, a great job. And now let's welcome Simon to talk us about analyticity in spin and causality constraints. Yeah, please, Simon, it's your turn.
Okay, so good morning, everyone. So first I would like to thank the organizers for what has been a great and exciting conference so far. I'm very sorry that I cannot be with you in person this morning. So I was on my way from Beijing to BIMSA earlier today when I received the first announcement. So this was just a very unlucky timing. So sorry about that. Yeah.
Yeah, no
And I turn
problem.
around.
Just stop.
Yeah. So I realized that not everyone in the audience will be familiar with quantum field theory. So what I thought is that in the next few slides, I would try to state mathematically what the main result is. And after that, I would go more slowly to the physics motivation and context of this result. Okay. So the main result is in the field of conformal field theory. I'm just trying to move that out of the way. Yeah. So the main data of a conformal field theory is a list of local measurements, things you can measure locally. These things fluctuate, but they have a definite scaling dimension and some spin, the way they transform under rotation. And conformal symmetry implies that these fluctuations have a scale invariant spectrum, so you have some power law. And they're characterized by an exponent, which we think of as a length, as the inverse length dimension of the measurement. And these measurements also have 3-point functions, which are very useful. And they are, I'm just trying to get something out of the way. They are, essentially, their shape is determined by symmetry, so they're basically just constants. This data basically determines all correlations between fluctuations on a space that's R to D. So this data is scaling dimensions and 3-point couplings via the operator product expansion. And the idea here is that if you have two measurements that are nearby, you can expand them and replace them by an effective measurement that combines them. And what appears in this expansion are exactly these 3-point couplings I talk about. So if you want to measure a 4-point fluctuation, for example, you can express it as a product of two 3-point couplings times some special function that depends on all these coordinates. That is a known special function related to the conformal group, so d plus 1, comma 1. And we write this operator product expansion in this picture on the right. It's not like a Feynman diagram. You're not supposed to sum them. Just one of these pictures, sum over all the intermediate scaling dimensions, give you the answer. Not supposed to sum over a channel. So now you may ask, is this formula make sense always? What happens if you choose a different channel? And that essentially is a constraint on this data. And this is a central problem of conformal field theory, is to find data, this list of scaling dimensions and 3-point couplings, such as the crossing equation is satisfied. So this crossing equation must hold for any choice of 4 points, any choice of external operators. So it's an infinite number of constraints on an infinite number of unknowns. In dimension greater than 2, in dimension greater than 2, this was met with limited success until 2008, but there was a kind of a breakthrough. And the idea then was to leverage unitarity, which is the fact that the unknown that appear in this formula, well, the thing that occur are quadratic in the unknowns, and they apply some positivity constraints. And using the sign constraints, you can really extract rigorous statements from this infinite set of equations. What we'll be discussing today is not so much in the context of statistical field theory, but in the context of quantum field theory. And so I come from a particle physics background. It's almost the same mathematics, except that you have to do a Wick rotation to insert some analytic continuation between the two worlds. But there's a new thing when you talk about physics that have a time direction. And the new aspect is that now when you measure fluctuation of fields, the operator ordering matters. Now we don't call them fields anymore, we call them operators. And one thing, for example, that you can check is that an important statement about field theory is that you cannot send information faster than light, and that means that the fields that are space-like separated commute. So that's an important property that only makes sense when you have a time direction. And the other sort of funny thing you can do when you have a time direction is that you can start talking about dissipation. And one measure, which is not entirely obvious that it measures dissipation, but we'll come back to that. It also appeared in Kitayev's lecture last week, is this out-of-time object, basically a double commutator. And so you have notion of causality and you have notion of dissipation. The main result we'll discuss in this talk is that using only this measure of dissipation, we can reconstruct all correlations. This is analogous to a kind of Kramers-Kronig relation, which reconstruct an amplitude from its imaginary part. And and we'll discuss how it enables to analytically solve the crossing equation in some limits. So I explain why we have this equation and why it's useful. But the main result is that. So you can reconstruct, if you know just the commutator, you can reconstruct the correlation function without the commutator. So I step back and give some motivation why we study conformal field theories, give some examples and context. So why we study conformal field theory? So I think there are two broad motivations. So they arise, first of all, they are in physics, they arise very naturally in statistical physics. Whenever we study a critical phenomenon, so what happens near a second order phase transition, when you tune the parameters of a system to a critical point, systems develop long range fluctuations that have these scale invariant and even conformal properties. And the other sort of main application is the so-called ADS-CFT correspondence, where conformal field theory, which is an object that we understand rather well, that has very clearly defined axioms, is equivalent to a theory of quantum gravity with one more space dimension. So basically, it's the only non-perturbative definition of quantum gravity we have at the moment. Very unique tool. And maybe some further motivation is that you can also view the study of conformal field theory as a natural step toward studying more general theories that don't have as much symmetries. And for example, any quantum field theory at short distance becomes, when you approach ultraviolet fixed point, becomes approximately a CFT. If you put any quantum field theory in this funny space-time antidecision space, it also gives you conformal correlation function. So there are close relationship between CFTs and more general theories that you may be interested in. So to elaborate on this example in statistical physics, so if you take a familiar system like water, if you boil it under very special circumstance of high temperature and pressure, so that you're close to this critical point, this is the point where basically vapor becomes so dense that it's almost indistinguishable from water. As you approach this point, when you're below this point, the transition occurs through nucleation of water droplets, and that have well-defined walls. But as you approach this point, the difference between the two phases become less and less significant, and the bubbles get bigger and bigger, and the walls get effectively less and less existent. So right at this point, there's effectively a continuum description that develops, and you develop these long-range correlations, and you can measure the fluctuations in the energy density or the pressure, and you find this funny exponent that is measured to have, for example, these numbers. And that depends, here you're effectively breaking, it's called a Z2 symmetry, because you basically, the system is choosing between two options, and you have two different exponents, whether or not you're looking at things that are odd or even with respect to this order parameter. And sort of amazing thing about this emergent behavior is that it actually has nothing to do with water. It really has to do with the system choosing between two different options. And you get the same exponent for different gases, magnets, and you also have different other sort of conformal field theories with other symmetries, which would describe other systems. So this sort of system can be studied in a lot of different ways. Monte Carlo, actual experiments. There are some analytic techniques, or at least approximations. And the technique I will be discussing today is based on the idea of this bootstrap. And the idea of this bootstrap is you want to calculate these exponents, which remember are determined by two-point functions in the power law of the fluctuations. The way we bootstrap them is by looking at more complicated object, four-point function, and using this crossing equation that I mentioned earlier. This figure here is one of the special function that is known, and when you multiply it by this unknown two-point coupling and sum over all of them, it's supposed to get 0 by the crossing equation. And the idea of the bootstrap is to manipulate this equation in order to find contradiction. So if you can arrange the external point or a combination of these equations such that you expect that the f squared on the left is positive. So if you manage to write something that's a sum of positive times positive equals 0, then you have a contradiction, and that means that some assumption is ruled out. So that sounds like weird. You're just like ruling out things, but the idea is you try to rule out everything except the theory. So for example, when you start making plot, these are the two possible values of the exponents, you can show that there's no consistent four-point function anywhere in the white region. So if some experiment were to measure a value of these exponents that's somewhere here, you'll say, well, that's not compatible. Something is wrong with that experiment. And of course, the actual model is determined by other techniques, is something you cannot exclude. So it's there, like you're on the tip of this little peninsula. So when you start seeing this plot like this, what you do is you add more and more constraints. And what happens, you start eating around this point. And when you get good at this game, you get plots that look like this. Now you've excluded everything outside of a little island. And the sort of slogan or statement you make from this is that, well, if a theory with this assumption exists, then its scaling dimension must be this number in this band. So that's how we use this self-consistency in Bootstrap to solve to calculate things. So now let me make a little bit less abstract this notion of what the set of measurements are. We saw two measurements so far, one that was even and odd. And in general, given any measurement, you can take a derivative of it and you make another measurement. But that's not very interesting and just has a dimension, like its inverse length dimension is increased by 1. Scaling dimension increased by 1 because derivatives as units of 1 over length. So it's very simple. When you take products of measurement, of course, that gives other measurements, but the scaling dimension don't add in a simple way because remember in quantum field theory, you cannot directly multiply things at the same time. You have to take a limit, renormalize. So in general, the things you get don't just have simple scaling dimension. However, there is something you can do which does give you simple operators, is if you multiply two things and stick a lot of derivatives between them, or precisely if you take transverse derivatives, so there's a lot of angular momentum between them, you're forcing these two measurements, A and B, to be relatively far from each other, and then the scaling dimension really just adds. So you have this is just a sum of the parts. So it's very similar to the to the energy of hydrogen states, which is the sum of the parts plus interaction part, which decrease with large spin. So we're saying the same thing here. At large spin, the interactions decrease. So that's something that many people had argued before the work I'm going to present before. Something that was well understood. And you can see it in data. So once you solve the theory, you not using the bootstrap or any method, you don't just get the scaling dimension of epsilon and sigma, the two things I plotted earlier. You also get all this other excitation, and you see that there's a lot of regularity and structure. So this is and you have the thing that shows nice structure is the scaling dimension minus the spin, because basically to increase the spin, you have to put derivative, so this is the combination that does not increase when you add derivative of the twist. Then you see this very nice flat curve. Okay. Flat up to low spin, but very flat at large spin. So now we'll move on and add a time direction to this story. So time direction arrives very naturally. It almost looks almost too trivial. So if you start with a rotationally invariant system, which is a function of distance in 3D, and you stick an I in front of one variable, it's called the Wick rotation, then mathematically you define another theory that has a time direction in Lorentz symmetry. So experimentally, these two systems are very different. One of them is called the 3D Ising model, and the other one would be called the 2D criticalizing model, 2 plus 1D criticalizing model. It's very different. One you have time, the other you don't have time. Theoretically, they're the same model. They actually have the same scaling exponents, same correlators. Like, so in particle physics, we use this Wick rotation all the time. Same correlators up to analytic continuations. But with the time direction, you can do more interesting experiments. And for example, you can test for causality, like I was mentioning before. And now let me make a little digression to talk about scattering amplitudes, which we don't have in CFT, but it's a good analogy. If we have a scattering amplitude, when you scatter things, like we do in collider experiments, you can ask if the outcome is determined. Yeah. Wait, let me say it again. Yeah. When you send the particles 1 and 2, the outcome that you measure at a fusor point 3, you should not get any signal before the fusor-like cone of particle 1. So the signal here should not ever faster than light at point from 1 to 3. And this property, here I'm skipping a lot of steps, but is well known to lead to analyticity of scattering amplitude. So causality and frequency space give you analyticity. So S is a center of mass energy square, so you get analyticity in that variable. And that is used to relate the complex S-plane looks something like this. You have the scattering amplitude, and on the side you have complex conjugate of an amplitude in a different process. And this analyticity gives you dispersion relations. So this is like Kramer's crony dispersion relations in optics. It's the same thing in particle physics. So this sort of formula are in particle physics. And now the point is that in CFT, you have a relatively similar picture. You don't quite have particles, but you can still do things that look like scattering experiments. If this is time and space, you can measure at correlations. You can look at correlation like this, and what will happen is that here you would create some kind of lump in the past that have spins lying one way, for example, and these lumps would propagate, they would go to each other, and then you can measure what comes out. But it should still be true that what you measure at point 3 is only affected by point 1 in its past. So it should not go faster than light from 1 to 3. So you expect some kind of dispersion relation also in conformal field theory. But to construct it, we have to find what's the analog of imaginary part of the amplitude and of dispersion relation. So the first one is relatively easy to guess. So if you take this analogy seriously between that this correlation function is measuring a scattering process, well, when you put them in time ordering, then here phi1, phi2 are creating a state, phi3, phi4 are absorbing a state in the future. So it looks like an amplitude, but it's really like a scattering matrix amplitude. It's an uninteracting part that we normally subtract, that's called 1, plus what we actually call the amplitude. Then we could put things in the other ordering, and then that would measure the complex conjugate amplitude, which somehow goes from the future to the past. But the thing that this appears in dispersion relation is the imaginary part of M. So in order to measure it, we need a third thing. That's like the 1. We need to get rid of the 1. Then if you add up these 3 equations, you get the imaginary part of M. And the left-hand side, like if you use that things are space-like things commute, the left-hand side is exactly a double commutator. So this is why this commutator square, the product of 2 commutators, is really a good analog for the imaginary part of amplitude. And you can also think of it as 1 minus a survival probability. So the amplitude here is 1 minus something minus IM. The imaginary part of M tells you, roughly speaking, how the real part is reduced. So it's really a 1 minus a survival probability. So it tells you about dissipation, absorption by producing funny stuff. So it's a nice object. And the fact that it's also 1 minus probability means that it's a positive quantity, it is bounded, and it does appear a lot in discussions of chaos. So we have this nice object, and now the analogy suggests that in any CFT, we should be able to reconstruct all the correlation function on the first line, given this thing in red. And now that's the motivation for, there was a motivation for the work that received the award. Now I will present you the formula that does that. It's actually a bit tricky to guess because it's actually impossible to guess because if I go back here to this formula, this you can sort of guess by complex analysis using analyticity. It's somehow relatively easy to guess this formula. But now the conformal correlator is really a function of two variables. It's a function of more variables. So it's really not so clear what the analog of this game is. So the key is to step back, and instead of getting the correlator, we'll get the OPE data, the scaling dimension and 3-point coupling. And again, I will have a slide as an analogy. So I guess if you come from particle physics background, this analogy would be useful. If not, I don't know how useful it would be, but in terms of group theory, it's a bit simpler. So this is in terms of a rotation group. So imagine you have a partial wave decomposition where you can expand an amplitude in terms of cosine. And then you plug this dispersion relation into the amplitude, you combine these two formula, and then you get this nice alternative formula that express the coefficient of the partial wave of spin J as an integral of the imaginary part of the amplitude. And somehow in this relation, the cosine, which was the spherical harmonics on a circle, got replaced by its Lorentz inversion, which is an decaying exponential instead of cosine. So this formula was discovered in the 60s. It's a cornerstone by Froissart and Gribov. It's a cornerstone of rigid theory. And its point in life is that answer that this partial wave at the top, it probably only makes sense for angles between minus pi and pi. But this formula answers that the formula continues to make sense when cosine of theta becomes in Lorentzian signature something that's greater than 1. So somehow when you go from one channel to the other, this formula, these partial waves continue to make sense. Then we can try to use the method of missing box. So if the symmetry group we're talking about is SO2, the spherical harmonics are just cosines, rotation in 2D, and the Lorentz inversion of this is exponential. In 3D, there's another formula where a Legend polynomial becomes associated Legend polynomial. That's a natural Lorentz inversion of it. And now we have to guess the same thing for the conformal group, which is SOD, 1, where now the conformal block depends on scaling dimension and spin. And now we have to find the SOD, 2 version of this. And okay, we can do many steps for this derivation, and I will spare you the derivation that I did in the paper, because it was not obvious. It was kind of a miracle at the end that it worked. So it's not a very pedagogical derivation. I will just skip it and present the result and see what it's good for. So the result is that there's some kind of work with block with inverted quantum number. And when you integrate this commutator square over a natural region where this commutator is non-zero, then you reconstruct all the conformal field theory data, at least except for spin 0 and possibly spin 1. This has to do with whether this integral converge or not. But that's the main formula. It allows you to reconstruct all the OPE data, all the conformal field theory data, from this commutator square. Yeah. So first application of this formula is that it really gives a simple way of understanding the OP data at large spin. And what happens, roughly speaking, is that the integral gets pushed to a corner where you can approximate it very easily. So a picture where you exchange nothing, identity, in the other channel. That gives you the uninteracting OP data with the scaling dimension that is just the sum of the parts. But then you can systematically add the corrections and understand how the physics and the scaling exponents, the coefficients, get suppressed by the 1/j correction at large spin. But this formula makes sense even for finite spin. So you can try to plot it all the way down to spin 2. And amazingly, it really works. This is in 3D Ising model. It really works well. Even when you reformulate this expansion not as a large spin approximation, but just as a simple way of approximating the integrand, it really works well down to small spin. So there's energy momentum tensor, which has scaling dimension 3. It's the energy density. So twist 1. So the formula gives you an organizing principle for the spectrum. Any operator with spin greater than 1 must lie on one of these continuous curves, which at large spin becomes something you can simply label. And in general, the interactions, which are the departure of this curve from a straight line, you can understand from cross-channel exchanges. It's a bit like the particle physics motto. We understand interactions from exchange of particles. Now these are not particles, but they're still exchanges. And yeah, this in some cases can combine this analytic understanding to get improved numerics. So I will sketch a few applications. So the other main application of this formula is to ADS CFT, which I will spend most of the rest of the talk on. And I will here just say a few words about some understanding that has happened since. So first question you could ask is, what the hell are these operators with non-integer spin? And it turns out that they are non-local Light-Ray operators. This was explained in this paper, which actually received a Frontier of Science award last year, like Simon Duffin and Kraft-Chock. So the simplest example of these Light-Ray operators is you integrate the energy momentum tensor along a light ray. That's energy flux, also known as average null energy condition. This actually is the integral of something local, but when you start taking operator product expansion of these things, you get non-local things that are generally non-local, that are continuation of these operators. Using this language, it's also possible to generalize the Lorentzian inversion formula to the case where you have all the operators have external operators have spin, you have all sort of quantum numbers. So yeah, it's very nice perspective on inversion. Something else which you can ask is, once you have this formula that extracts the CFT data in terms of double commutators, you can try to resum it and get the correlator from the commutators. And the scattering amplitude, it sort of works nicely because of identity like this. So the thing that extracts the amplitude is this associated Legendre function Q. And when you resum the parapartic expansion with the correct weight, you get exactly the kernel in the dispersion relation. So when you do the same game in CFT, you resum, so you take the inversion and then you resum the OPE. You get a formula that reconstructs the correlator from its double discontinuity, exactly as we wanted. But then the kernel is really not something you would have guessed. It turns out to be involved. It's a function of 4 variables, and but somehow it factors through this mind-boggling combination of variables. I would have never guessed this. It just comes out of resumming. But yeah, essentially this formula exists. But the way it's useful in practice is conceptually. The fact that it exists is conceptually useful. So the way you use it in practice, all you need really is the dispersive transform of one block in the other channel. And that turns out to give you exactly a Witten diagram, which is somehow it represents exchange of particle propagating ADS with a specific mass and spin. So somehow we've arrived at a way of writing correlation functions that involve particles propagating ADS. It was not obvious a priori that you could get that, but this is what comes out of this formula. So the So this is the contribution of a single block to this dispersion relation. So I will come back. So this formula would be useful later when it's kind of a stepping stone toward talking about holography. Here, it's just kinematic. You can apply this, you can use these within diagrams, these Polyakov rigid blocks, you can use them in theories that are not holographic, and they just work, they're just kinematical objects, but they're a good stepping stone to holography. And maybe another application that's sort of one of the important points of rigid theory, of continuing things in spin, is to understand the physics at very high energy, large boosts. And that was the main motivation of rigid theory initially, to study forward scattering at very high energy and strong force. And then we can do the same for like the Ising model. And you can characterize the high energy or the large boost behavior of objects by an energy to things would go like energy to an exponent j star minus 1, where j star is the minimum of this curve. So we've estimated the exponent 0.8 in this work. And the fact that this exponent is less than 1 is very significant. So this j minus 1 is really like a Lyapunov exponent. And this is telling us that in this model, when you take spin lumps and you scatter them with more and more energy, they become more and more transparent, which is very opposite to what happens in other models in particle physics. But this is what will happen in this 2+1 dimensional Ising model. So that's a prediction we've made. There's no experimental realization yet of the 2+1 dimensional Ising model, so we don't know, really have no way of testing this at the moment, but that's a prediction we can make from all of these predictions. So let's say a few words about holography now. How am I doing on time?
Yes, I think you still have like 28 minutes.
Oh, okay. I will be done before that. Yeah.
Yeah,
So
that's okay.
yeah. So the other main application I think of this formula is it's really shed light on holography. So holography is this relation between a conformal field theory, a sort of familiar object, field theory in d dimension, and an object with quantum gravity in one extra dimension. It was conjecture 97 by Mendocino. It came from studying black holes in string theory, but it's now really been abstracted from the setup, and it's really part of the theoretical landscape. Yes. So an important conjecture there is that you can ask in which theories do you really get an emergent extra dimension? Which field theories have this property? So I think if you take any random condensed matter system that's strongly interacting, it's really not clear what happens. But in the case where relativistic invariance, we believe we understand the criteria. So it's a theory that needs to have many degrees of freedom in the sense that the 2-point function of the energy momentum tensor is large. And it needs to have no higher spin operators below a certain scaling dimension. That's called a gap. It needs to have a large gap for higher spin spectrum of so-called single trace operators. I'll come to that in a second. So this conjecture that the theory of this property, so basically a large gap, to make it short, is dual to classical gravity in the bulk. Classical gravity means that it's an effective theory that's Einstein gravity up to length scales that are small, suppressed by 1 over this gap. So scaling dimension is like energy in the bulk. So this is a length scale.
Hi, Simon.
Yes.
Yeah, I got a question. So here, the boundary field theory looks like has not too much constraint. For example, any symmetries
Yeah, it needs to have
other than
a
other
it
than the
needs to,
red.
it has a conformal symmetry. Yeah, relativistic and conformal invariance. Sorry.
Okay, okay.
Yeah, sorry, I should have written yeah.
Mm.
Yeah, there's something like a non-relativistic conformal invariance that it's not clear how much it buys. But I'm talking specifically about relativistic conformal invariance. Sorry, I've written the word. Yeah. And so, but you need the theory with large number of degrees of freedom. So basically, the 3D Ising model here fails this criterion, because it's a 2-point function of t is order 1. And you need also this spin gap. So a weakly coupled theory typically does not fail this later criterion, but a strongly coupled theory can pass this criterion. So normally what happens in the SCFT is that the theory and the boundary is strongly coupled when the one on the bulk is weakly coupled. So normally it's a weak-strong duality. So these conditions are relatively long to spell out. However, it turns out that they're exactly the conditions that make this commutator square simple to calculate. So let me explain why that's the case. So this notion of a single trace, so the idea is that, so why does a commutator suppresses so-called double trace? So normally when you take the operator product expansion of two fields phi, in the theory with some kind of large N expansion, you'll get double trace and single trace. But the double traces, they basically have scaling dimensions that are the sum of the parts plus small corrections, just like what we saw at large spin. This also happens at large N. But then when you take the commutator, the commutator is taking a discontinuity. You're making this distance time lag, so the sign flip, and you pick some phase factor. But when you take the discontinuity of something that's an integer power, you don't get the discontinuity. So the discontinuity is proportional to the interaction part. So when you take this double commutator, it's very much suppressed in the 1/n expansion, and you don't see it to leading order. So this double discontinuity is completely insensitive, well, to a very good approximation to the double trace, and it's saturated by single traces. And what happens in this theory that we conjecture to be holographic is that basically you have very few single traces. So that means that this double commutator is easy to calculate. So what this does in practice looks like that. So you can draw a picture. So what we're saying is that this double commutator, we can interpret it as giving you the imaginary part of a bulk particle. This is a non-trivial statement. So what this means is that, remember that the strongly coupled field theory doesn't have any quasi-particles. What this is saying is that if you ask how energy is dissipated in that theory, you're not producing quasi-particles. However, it turns out that you produce particles in this bulk of ADS space, this emergent spacetime. In one extra dimension, you produce actual particles there. So the theory doesn't have quasi-particles in the usual sense, but it has quasi-particles in the bulk. That's what this formula is telling us. And this double discontinuity will give you a simple way of calculating this. And what happens is the Lorentz inversion formula, or this expansion in terms of Polyakov rigid blocks that I mentioned, dispersion relation, basically reconstructs the correlator using these things in two channels. So it's exactly what you would get if you had a dispersion relation in the bulk of ADS. Reconstruct the amplitude from its imaginary part in two channels. That's exactly what happens. So it gives you a concrete way of calculating something that happens in the field theory. This G on the left is a CFT object, but you compute it in terms of exchange of particles in the bulk. But all of this is derived from the field theory. So at tree level, for example, in supergravity, it's very simple. You just exchange supergraviton, graviton multiplet. So you just have some finite number of diagrams, graviton exchange and scalar exchange. And the thing you get out of this inversion formula, you reproduce precisely a difficult calculation that was done before using tree-level Feynman rules of supergravity in S5 cross S5. And the other thing that comes out is you can control the correction. I will come back to that. But yeah, and it also has been generalized to understand all sort of spherical harmonics on the S5, all sort of developments here that I will skip. But there's some very nice structure in these objects. This works at loop level. So now if you start including the double trace that I said are suppressed, they're suppressed, but they really represent one loop correction. So you can try to calculate them. It still works. You calculate this double commutator at the next order, and you get, it works like the Kotkowski rules. It's like in the double discontinuity of a one loop diagram in the bulk is a product of three diagrams. And this has been used to calculate various even two loop results for 4-point correlation functions, 5.3. And just a message I want to get out here is that it's really striking here is that usually the point of the ADS-CFT duality is that it's easier to do calculation in the ADS space. When the CFT is strongly coupled, you go to the ADS description, which is weakly coupled, and it's easier. With this formula, it's turning the duality on its head. It's actually very hard to calculate these loops in ADS, but on the CFT, we can do it. So working directly in the CFT is actually advantageous with this formula. Yeah, maybe this is my last slide, effectively. So the sort of thing which I find really striking, and it was the main part of this conjecture by, I mentioned before, by Polchinski and friends, is that when you have a large gap of IO spin, this large gap that I mentioned of IO spin operators, it turns out that this construction, when you look at the amplitude for stress tensor in the boundary, we can only give you the result as if you had Einstein's theory, Einstein's gravity in the bulk, Einstein general relativity in the bulk. You don't get any modification to it. You really land on Einstein theory, nothing else. And the reason that this works is that this dispersion relation allows you to write some rule for Newton's constant in terms of probabilities at scaling dimensions that are large delta gaps. So it's like large energies. So you can relate the low energy measurement of Newton's constant to high energy processes with positive coefficients. And then you get similar sum rules for all the corrections to Einstein gravity. But just by dimension analysis, they come with suppressions by extra powers, which are suppressed by 1 over delta gap. And using this observation, we can really get rigorous bounds. For example, this Gauss-Bonnet coupling is a Riemann square correction to the Einstein gravity action. And 5 dimension, for example, in the bulk, we can bound it. And to be a precise number, this 23 is just something that comes out of the numerics divided by this gap. So in a theory with a large gap, this is small, and you really recover Einstein's theory plus a negligible correction. So it's one of the striking things. The only thing you can get is general relativity and nothing else, plus small corrections. Corrections have to be small. And maybe this is my last slide. So yeah. So the way this works at the end of the day is that in ADS space, causality is a very sharp statement. And like we use that on the boundary. So this is again the depiction of the ADS-CFT correspondence. The CFT leaves at the boundary, the ADS in the middle. And the fact that you have causality on this boundary theory really means that signals can never go faster through the boundary than through the bulk. Otherwise, you will violate this commutator statement. So physically, that means a signal should not be able to go faster through the bulk. And that's classically a statement known as the Caron Huot theorem, but it's an exact statement in the CFT. And what we've seen through Lorentz inversion formula and dispersion relations is that when you take the radius of ADS to infinity, this statement reduced to a dispersion relation that is satisfied by quantum gravity S matrix. So this shows that the people have it's been questioned whether quantum gravity in S matrix in the flat space limit. So RDS goes to infinity, it's a flat space limit. So people have questioned whether the S matrix of quantum gravity should be exactly satisfied this relation, or maybe you could have time advance that are like Planck time, things like this. This shows that in dispersion relations are compatible with quantum gravity. You don't need to have such time advances. That's one of the lessons. So here's an outlook and summary. So we discuss dispersion relations for CFT data and correlators. Input is unitarity of the CFT and causality. Its output gives you some large spin expansions where you can control the errors. It allows you to explicitly calculate all sort of 4-point functions in ADS-CFT. And you get bounds on higher derivative corrections of the effective theory that really encode the fact that the bulk theory is local. So I think more generally, there's much more to be learned from dispersion relation, not just in ADS space, but also in Minkowski space. Would be good to explore. We see that what you tend to get from dispersion relations are Einstein gravity plus small corrections. I think it's interesting to explore more systematically the landscape of consistent gravity theories. There's been a lot of conjecture actually about this landscape, as was discussed by Kumrun Vafa's talk last week. And yeah, it's still a very open direction to really make contact with the conjectures. And also we learn a lot about conformal field theories, but now we're getting mature enough to try to tackle theories that are less symmetrical, maybe having a strong force. So hopefully that's what's going to happen in the next years with the new generation of work. So thanks everyone.
Okay. Thanks, Simon. Thanks for the good talk. Yeah.
Oh, I just see that there were questions during the talk. Sorry.
Uh-huh.
There were questions, but maybe people can ask their questions again.
Yeah. Are there any questions in the audience? So if not, I have a very maybe silly one because
Yeah,
I'm not in this field. So here you care about the large spin expansion a lot. So for the low spin, it's very well understood already.
Yeah, so I think what happens right now, I think it's not completely satisfactory, but right now the somehow viewpoint is that you can sort of, in some theories, at least some case, you can trust this large spin expansion down to a smallish thing, even like spin 2, or maybe even spin 1 in some case. But then you need some other numerical technique to get the spin 0 ones, which are kind of a distinct world.
Okay. So analytically, it's still not solved.
Yeah, so you don't. Yeah, so we don't get down to spin 0. It seems so. This theorem it only guarantees that things with a spin greater than 1 lie on these trajectories. So this approximation does seem to work in this case, but theorem guarantees nothing about spin 0, and in practice, it does seem that spin 0 is disconnected.
Okay.
So I'm trying to. Okay.
Are you in the room?
Okay. Hi, Simon. Sorry, I guess the technology is a little bit complicated here because very nice talk. I have two questions for you. One, you said something about 2 plus 1 dimensional Ising model. You said we make a prediction. I don't know which hasn't been tested. So I didn't follow that. I mean, what is the prediction and how can this be tested for 2 plus 1 the Ising model?
Yeah, let me say it. So, but first of all, you have to find we need two things to test it. So you need, first of all, you need to have a realization of the 2 plus 1 critical Ising model, which I've heard is some people may have something close to it, but it's not yet settled. Then the next thing you need to be able to do is to be able to prepare something like a region of spin up. So you start from the disorder state, and you prepare a little lump where the spins are up. And then you need to be able to accelerate this lump so that it gets to move close to the speed of light.
Accelerate it in an Ising model. I mean, Ising model is like a lattice. So what is the accelerated?
Yeah. The lattice sites stay there, but you want to have a kind of spin wave.
Okay. You want to accelerate the spin. Okay.
Exactly. So you want two spin waves that go close to the speed of light, and the claim is that they would just go through each other at high energy.
Okay. Interesting. So you have a prediction for that. Okay. So that's very cool. So I don't know. I mean, it sounds like an interesting challenge for experimentalists. So maybe we should talk to someone to convince them to do that. So I have another thing regarding related to the last part of your talk. You mentioned this Bark locality that comes out of the properties of CFD. So how would you solve the black hole information paradox if you have Bark locality?
Yeah. So I think the short answer to this is that we see bulk locality in the simple correlation function. Here we're studying like 4-point functions, and we see that they are the same as you would compute from a local theory of Einstein gravity. Now, if you want to do now, if you want to talk about an experiment which tests the information paradox, you have to look at much more complicated objects. Like you take two operators, you create a black hole, and then order of S arcing quanta come out, and then you do a measurement of all of these quanta. So you need kind of a S point function.
Hmm.
And this S point function is order e to the S options for what you can do, which is the entropy of the black hole. So the information paradox comes from studying correlation functions that are infinitely more complicated than what we study. So we really have nothing to say about that.
I see. So you're saying that this statement about locality is just for like simple correlation functions, but at some point, if it becomes too complicated, then it's not clear what it means. So that's what you're.
Exactly.
Okay. Okay. Very good. Thank you very much.
Thank you, Simon. Yeah, and also thanks for the questions. Yeah. I have one last question, if it's okay. Yeah, can you explain a little bit more to you mentioned about the swampland conjecture stuff. So
Mhm.
so can you say, for example, what kind of constraints can you put
Mhm.
on
Yeah,
the swampland conjectures? Yeah, yeah.
Yeah, so so some of these constraints, I think this is so at the moment we have not. So this is still speculative. So it's outlook. So yeah, I mean, make some statements that we can sort of, I believe, hope to make progress on. So for example, there are conjectures about what happens at this cutoff delta gap. So one conjecture that is called for example, called the emergent string conjecture, is said that the only thing that can happen at the scale is the scale that represents the Planck scale of some higher dimension physics or string theory. So we can try to constrain what happens at the scale and see if it fits in these two behaviors. So that's one thing we can try to do. There are also constraints about how this, when you have a family of conformal field theories that are labeled by some parameter, they're also constrained on how this scale delta gap changes with the parameters. So this I believe are things we can probe. We've not yet obtained any useful theorems along these lines, but these are things that can be probed using simple correlation functions, and therefore we can try to study them.
Yeah, very interesting. Okay, very interesting. Okay, thank you, Simon, and thanks Nash for very good questions. Yeah, okay. Then I think we can finish this session. Yeah, bye. See you
Hi,
soon.
everyone.